let's take a little bit of a look at how, so the first step is to identify that this is an electrocyclic reaction. And the way you know it's an electrocyclic reaction is because it's either a diene or a triene that is just sitting with a reaction arrow. There's no other reagents present. And so that's how you know it's an electrocyclic. There really is no other reaction other than the paracyclic reactions of either sigmatropic, cycloaddition, or electrocyclic, where you just have this organic molecule sitting in solution undergoing a transformation. At least none that we go over here in sophomore organic. Once you realize that it's an electrocyclic reaction, you just have to look for that flow of electrons. So these are going to come down and form the new sigma bond right here, which means these have to move out of the way, moving over to form a new pi bond there, which means these have to move out of the way and form a new pi bond here, which helps fills in the gap that's left when these pi electrons move over to form the sigma bond. So it's going to have this, if you count the carbons, 1, 2, 3, 4, 5, 6 carbons that are going to now be in a ring structure because you form the sigma bond between this carbon and this carbon. So they're going to have this ring structure like this. And if we number them, 1, 2, 3, this isn't locants, but just to keep our head straight about where everything is. 1, 2, 3, 4, 5, 6. That means that this carbon right here is going to have a double bond, or these two carbons, the 2 and 3. The 4 and 5, as I numbered them, are going to have a double bond because that's where this moved over between 5 and 6 to 4 and 5. And the double bond between 3 and 4 originally moves over between 3 and 2. And then on the number 3 carbon is this methyl group that's sticking out. Now the last thing that's left, and that's where you have to do a little bit more analysis, is to figure out, the last thing that we have left to figure out is where do these two groups, and these can be methyls, they can be OCH3s, they can be really almost anything. I don't get too crazy with it because I'm not sure at what point there's some limitations where other reactions might actually be more dominant because of that R group being different than something simple. So it'll usually be alkyl groups or or alkoxy groups, ether type structures. That'll be at these positions. But they are, in this case, they're methyls, CH3, CH3. You don't have to draw in the CH3s, but sometimes that helps people, so I thought I'd show it right here. Just like this is a methyl right here. So it's kind of left with what is the stereochemistry of these groups? Well, they're there at the 1 and 6 carbon. There's also an H here too that's hidden. It's not drawn out. And so the question is, where are they located? Where are they positioned? Are they on wedges or dashes? Because remember, these are sp3 carbons, meaning they have a tetrahedral shape and it's in a ring structure. So the two other groups that are at these positions are pointed up or down. So we have to figure that out. So there are two ways to do this. So after you identify that it is an electrocyclic reaction, and then also draw kind of what I would call like the backbone or the fundamental shape or structure of the product, you have to then determine the position of those groups connected to it by analyzing whether the rotation of the carbon atoms, the two end carbon atoms that are forming the sigma bond, whether they're rotating conrotatory, that is, in the same direction, or are they rotating disrotatory? Just to clarify real quick, conrotatory and disrotatory, those end carbons, in order to form the sigma bond, they have to rotate in order to overlap the two p orbitals that are part of that pi system that are on them. They have to rotate those two p orbitals, one on each carbon, onto each other, and it has to be it has to have that conservation of phase symmetry, or it has to have the correct phase of the lobes to overlap. And that's what we'll get to in a second, how you or one way you can analyze it. But just to clarify, what's conrotatory as these carbons are rotating? If it's conrotatory, that means they're going to rotate the same direction. Like this. Or let's say you had two groups that are opposite each other, it would look like this. Because notice, I just want to show you the trick that your eyes can deceive. These are rotating the same direction. Because if you think about it, this is rotating, think of this is rotating clockwise, but this, if it rotates like this, that's also clockwise. So that's why I drew these two arrows. By the way, these aren't two different ways to rotate. This is the same thing. This is a clockwise rotation. It's just two arrows showing like the top going this way, the bottom going this way. That's a clockwise rotation. This is a clockwise rotation. The whole idea is that if this carbon's rotating clockwise, then this carbon also has to rotate clockwise. That's conrotatory. For disrotatory rotation, if one of the carbons is rotating clockwise, then the other carbon has to rotate counterclockwise. So if we had two things like this, I put these are weird structures. They don't mean anything. I just wanted to give you something to kind of see the rotation. So if this is rotating clockwise, this one also has to rotate clockwise if it's disrotatory. And then let's say we had some kind of arrangement look kind of like this. This is all abstract, but if this is rotating clockwise, then this has to rotate counterclockwise in order for it to be disrotatory. So that is disrotatory rotation. Now, it isn't limited to, don't get confused and think that conrotatory means both always rotate clockwise. You can also have them both rotate counterclockwise. So it'd be something like both of them rotating like this. The whole idea is that whichever way the one carbon is rotating, if it's conrotatory, it has to rotate the same direction. The other carbon has to rotate the same direction if it's conrotatory rotation. And if it's disrotatory, it has to rotate opposite. So it doesn't always have to rotate in this one clockwise and this one counter. It can be this one counterclockwise and this one clockwise, like that. So just keep that in mind. The whole idea is conrotatory means the two carbons are rotating the same direction. And I spelled this wrong. And disrotatory means that the two carbons are rotating opposite directions. To determine whether it's rotating disrotatory or conrotatory has to go in kind of to the first principle of the whole reason why the carbons are rotating. That's to form that sigma bond, which is going to be an overlap of the two end p orbitals. So if you think about these molecular orbital diagrams, these points where these p orbitals are at, these are the carbons. And so this is the diagram that represents 6 carbons in a conjugated triene structure, and the molecular orbitals representing the pi system of that triene structure. And the end carbons that are forming the sigma bond are going to be these carbons right here at the end. And so it's these p orbitals that are going to be overlapping that you have to concern yourself with what their phase is for the lobes, the two lobes on each one of those p orbitals that's overlapping when they rotate. So the question really comes down to, it's always the highest occupied molecular orbital that you're looking at the p orbital, the end p orbitals for, to determine that rotation. And so the question always comes down to, right now this is the highest occupied molecular orbital for the ground state. For the excited state, it would be the one where the electrons have promoted in this format right here, where this has gone up here due to light. So if light is used, this promotes up. And so now this is the excited state, highest occupied molecular orbital. So you're going to look at psi 4 if you're using light, and if you're using heat, psi 3 for the ground state. Because if you're using heat, there's no excitation, and you use the original highest occupied molecular orbital. And so that just determines, are you looking at these two p orbitals that have the two signs pointed, the two same sign lobes pointing in the same direction? Or are you looking at where they're flipped on opposite sides? Say we're looking at heat. So what is our two end p orbitals going to look like? Again, if we're using heat, then we're going to be looking at the ground state highest occupied molecular orbital. And so the two end carbons are going to have p orbitals that look like this. We don't really care about the rest of the p orbitals. We only are interested where the what the signs are of the lobes on these two p orbitals relative to each other. That is, these are clearly the same sign because they're shaded the same color. These are on the same side, quote unquote, of the carbons in the ground state, highest occupied molecular orbital, whereas in the excited state, this darker shading would be down below. That affects the rotation that is required for these carbons in order to overlap these same two lobes, or these two lobes. It doesn't matter. The whole idea, it doesn't matter if it's the darker shaded or the lighter shaded. It just matters that whichever lobes you try to overlap to form that new sigma bond, they have to be the same sign. With these lobes the way they are, in order to overlap, you have two ways to rotate. And if you notice, it's going to be, in one of the ways, you're going to rotate this direction, move this lobe down. And in this one, you're going to move this direction to move these two down so that it looks like this. Not perfect overlap, but I'm just trying to give you a general idea. The other way you could rotate is to rotate these these lighter shaded lobes this way, which would lead to this arrangement. Once again, it's a really horrible overlap, but I'm just trying to get the idea about where the two lobes are. So in both of these cases, if you notice, they're rotating opposite directions. This is clockwise, this one's counterclockwise. And so in both of these cases, in order to overlap the same sign lobe, these are both examples of disrotatory rotation. In other words, you're either going to rotate clockwise or one is going to rotate clockwise, the other one counter. Or maybe the first one rotates counterclockwise and the second one rotates clockwise. But the whole idea is this one rotates counter, this one clockwise, this one counter. But the main idea is these are rotating disrotatory. Finally put it all together because okay, I know it's disrotatory. Maybe I use the Woodward-Hoffmann rules and figure out it's disrotatory, which I'll show you in a second. How do I know where do the two groups end up? Get to the point. I want to draw the final structure. Once you know they rotate disrotatory, it all comes down to where the two groups, or maybe there are really four groups because of those hydrogens. They could be something other than hydrogen, but where do these groups end up relative to each other? Well, if they're rotating disrotatory, I'll do it in a way now where you can see both the orbital overlap and where the groups end up. Now, I've made these so that the four groups, the two hydrogens and in this case the two methyls, are located relative to each other the way they are. If you're looking at the ring, well, it's not a ring yet, but the triene in that rotated form that we showed, I took the other pieces off because it's really crowded, but imagine a bunch of stuff here that's hidden. But we're looking down the two bonds kind of being held at each other. We're looking straight on at those two end carbons. And so in order to rotate, once again, we're going to either rotate one counter and the other one clockwise or vice versa. Let's see what happens when I do that. I'll rotate ones like this so that they overlap. And so as we can see, when they start out pointed, so to speak, away from each other now, and we're doing disrotatory rotation, they move into an up position, both of them. And then if I rotate the other way, but it's still disrotatory, one counterclockwise, the other one clockwise, they both end up down. One way you can draw that is the following. I don't have molecules kits. Well, I guess you do. It doesn't take home a test, but they're not necessarily as nice as those. How can you do it on a sheet of paper? Well, once you know it's disrotatory rotation, now ignore the p orbital, because we don't need those anymore. We've already analyzed it, or maybe use the Woodward-Hoffmann rules. Now you just have to keep in mind, how does this look if I'm looking straight down those carbons in that conformation? They look like this. So if I know the two ways it's going to rotate is either counterclockwise, clockwise, or clockwise, counterclockwise, then that's what's going to happen. Let's say this one rotates clockwise, so this moves up and this moves down. Then this one has to rotate counterclockwise, which means this moves up and this moves down. Notice the idea that this is a counterclockwise rotation, and this one is a clockwise rotation, and that would be disrotatory. So these are moving disrotatory, which is good because that's what the carbon we've already proved is going to do under the scenario that we are analyzing. And so when it does that, we're going to have a new sigma bond form between these two carbons, and now the two methyls are pointed up, and the two H's are pointed down. So what does it mean? It means this one is going to be pointed up, and this one is going to also be pointed up, like this. Now, you don't have to do the full analysis for everything in order to figure out the product, because it's always going to be the enantiomer, or if you think about it, if you draw the first one, do the full analysis, and realize one is going to be up and one's going to be down, then you just flip them. Same thing here. If you find through the analysis of the one set of disrotatory rotations that the two groups are going to be on the same side, maybe pointed up or both pointed down, you just know automatically then that the other product that would form by doing the opposite set of rotations, still disrotatory, are going to be where they're both pointed down. So those are your two products for this electrocyclic reaction. First, we identify that it's an electrocyclic reaction. We kind of get and by doing that, we usually have the bare backbone of the new ring that's formed and where the double bonds are and any other of the groups that aren't on the end carbons that are rotating, where they're located. Those are always sp2 carbons, so there's no stereochemistry to them. I mean, there's no RS stereochemistry in wedges and dashes. Then we have to determine which way it's rotating, so we can figure out where those groups on the end carbons end up. Are they wedges or are they dashes in that new ring structure? I showed you the analysis of orbitals. Let me now show you the Woodward-Hoffmann rules, which is really quick actually, because remember in this step we're just trying to determine whether it's con or dis rotatory. Here we have the Woodward-Hoffmann rules summarized. So the whole key to this is you're going to try to figure out whether or not you are conrotatory, disrotatory by looking at the same thing, really. You're just not diving deep into the analysis of the orbitals. You're just realizing there's a trend that happens then. That whenever you're dealing with the triene, for example, and its molecular orbital diagram, you always get the same rotation type, whether it's thermal or photochemical conditions, and the same for when you're dealing with the 4-pi electron system or the diene system. So you don't always have to go to the orbitals. I just like that because also that's the only right way to explain. If I do a problem where it needs you to fully explain why dis and conrotatory rotation is what it is for your system, you don't just say the Woodward-Hoffmann rules. Those were just two scientists summing up their observations. The explanation is what I just showed you with the orbitals. But if you are just being asked for the product, like in one of my product synthesis problem, then you can just jump straight to these rules to figure out what the rotation is, so you can quickly figure out whether the two groups are pointed in the same or opposite direction based on that rotation type. So for our problem, how do we analyze it? Well, because it was a triene, in other words, a 6-pi electron system, we're going to be looking at this row right here, and then it really comes down to, is it thermal or is it photochemical? And so in our case, it was a 6-pi electron system, it was a triene, and it was a thermal condition, it was heat. So it's disrotatory rotation. So that's really, you see my thing, what? That's quick. Why do you make me do those orbitals? I don't make you do them if you're just trying to figure out the product. However, if you're trying to explain why you get the products that you do, which is ultimately why is it disrotatory rotation in this case, you do have to mention the orbitals and kind of explain then also what looking at the orbitals tells you. The idea that it is trying to, the whole idea is it is trying to rotate the two NP orbitals onto each other in a way that the symmetry matches of the signs of those lobes that are overlapping in those two NP orbitals, as I just walked through and showed you. So if you're trying to explain, you definitely have to go the p orbital, the molecular orbital end p orbital approach. But if you are just trying to figure out the products and there's nothing else being asked, then you can just use the Woodward-Hoffmann rules to figure out the type of rotation. You still, once you know what type of rotation it is, have to consider what that means for how it's going to rotate your two end groups. Don't assume if it's disrotatory, they're always going to end up cis or on the same side of each other. That only was the case because of how our structure looked initially. Where these two groups are relative to each other affects, essentially, where they're located in this diagram when you're looking head on. So in our case, they're pointed out. Once you know how they're positioned relative to each other on those two end carbons, the fact that it's disrotatory in this case does mean that the two methyl groups are going to rotate up, both of them up, or both of them down, depending on which way you rotate, disrotatory-like. And so that is only the case when they're pointed out. If one was pointed, if the methyls were switched and a methyl was here, then rotating disrotatory, which is these arrows I've drawn, would mean one methyl would go up, the other methyl would go down. They'd be on opposite sides. So you can't just think disrotatory, cis, or something like that. You still have to think carefully about how do my groups, those four groups, how are they located on those end carbons? You know, where are they exactly located? Because disrotatory motion isn't going to just mean this. It's going to mean that these outer groups for disrotatory rotation are going to rotate one counterclockwise up and the other one counterclockwise up. And these two inner ones are going to both rotate down, or vice versa. You can also rotate this one down and this one down, because that would be this would be clockwise and counterclockwise. So the whole idea is there's two ways to rotate within the concept of disrotatory motion. And it matters where everything is when you do the analysis, even with the Woodward-Hoffmann rules. So you do have to think it through. You can't just memorize or think, ooh, that. Well, I hope this analysis was thorough enough. This is how you'd analyze it. This is how you figure out what your product is in these steps, as I kind of wrote out for you again. You identify, first of all, that it is an electrocyclic reaction. Then you figure out, is it con or disrotatory, by either using the Woodward-Hoffmann rules or looking at the molecular orbital diagram and figuring out which two end p orbitals you're looking at and how they rotate so that they overlap correctly. Then once you know whether it's dis or con rotatory, you then have to go through the analysis of what does that mean for those four end groups? Where are they going to be located if they are rotating that way in the formation of that sigma bond? So what are the two products? And that's what leads you to finally get your final answer. Well, I hope this was helpful, and I'll see you all in class.